there anyone who has not used LinkedIn? Okay, no one is trying to escape from all these companies who are tracking you. So if you haven't looked familiar with this page, so if you look at all the things that are available on LinkedIn, so you have a member, you have jobs, you have ads, posts, company course, most of you are familiar with all these things. But there are these tiny little numbers that you can probably, is this working? Probably not. So you can see some of the numbers out there and all the analytics that you can see on LinkedIn. So today what we are going to talk about is how do we generate all these analytics out of all the things that you guys do on LinkedIn. So let's look at what is someone doing on LinkedIn most of the time. So the entire LinkedIn activity is modeled in an actor, verb, and object model. So you can think of a user, a recruiter, or a representative as an actor. And a verb is basically what you do on LinkedIn. So you might either comment on something, you might like an article, or you can do any of these actions on one of these objects, right? This is basically the fundamental unit in terms of how activity is tracked on LinkedIn. In fact, this is so important. If you followed the recent news, LinkedIn even added few more things that you can do. So you can now like, celebrate, love, insightful curiousness. So all these new things have come up, and this is like really the bread and butter, and a lot of things are built on top of this. So today's talk is mainly about this, on how does LinkedIn take all this data that is coming in from various different users, and how do we convert all these things into beautiful products that help LinkedIn grow. So the ultimate goal of any company is to basically get into this everlasting life cycle, which is you build products, the product generates data, and you use that data to generate more insights. And last but not the least, you use those insights and create more products. So you are always in this cycle, and you're generating more and more engagement, better products. So this is exactly what we did at LinkedIn. We used this data, and if most of you might be familiar with this, if you have used any charts at LinkedIn, on LinkedIn, which is who viewed my profile, or if you have published an article, and if you have looked at how many shares, where did it come from, all these slicing and dicing feature, most likely you're using something behind the scenes, which is Pinot. So Pinot pretty much powers almost 50 plus site-facing applications on LinkedIn. More or less 30 plus are in real time. So if someone looks at your profile, you immediately get to know that there is someone else. The tick basically goes up, and then you get the slicing and dicing on the data. And you have talent intelligence, which allows you to look at how the competitors are doing, what is the distribution of your workforce, and all these things. So you have billions of records here, terabytes of data. All these things are powered by Pinot. There are also a lot of internal products that are powered by Pinot. So the experimentation platform, the anomaly detection, and also lots of other internal apps are also powered by Pinot. A quick intro about me, for those of you just got in. So I've pretty much worked on a lot of Apache projects, and these are some of the projects that I've created over time at LinkedIn. So Apache Helix is the cluster management framework used to build a lot of various distributed systems. Pinot is the OLAP data store that I'll be talking about today. Espresso is the document store at LinkedIn, which pretty much stores all the profiles, and it's the source of truth. ThirdEye is another project that I recently started working on, which helps you do anomaly detection and root cause analysis on top of all the time series data. Recently, I left LinkedIn on last year, December, end of last year. And I wrote this article. And I have to confess, this was the first time I actually published an article on LinkedIn in 7 years. And it just took 7 years for me to publish this. So it was a really wonderful journey for me at LinkedIn. I loved every bit of it. And I really had to write this to just express my gratitude to LinkedIn. So you kind of get all these analytics once you publish your article in LinkedIn. So you know how many people viewed. It's it's very funny that a lot of people from Google viewed it than LinkedIn, but that's what the data says than what I think. And then where did they come from? What are their geolocations and things like that? So the first thing that I will basically take up is how did we actually come up with this? What happens behind the scene to power such a thing? So in case if in your company you have this activity stream, activity data that is coming from your users, what can you do with it? And how do you build a product that can actually take the data and build more products? So the first use case that I'm going to talk about is providing analytics on this article views. So let's start with the simple premise. You have a user who is looking at an article, or he might view it, you might like it, share it, do whatever actions that I mentioned earlier. The first thing that we have is you have a stream that is just saying someone liked something, right? That's pretty much the way every activity or event is represented in LinkedIn. So the traditional approach of solving this is you take this data, put it into a database. You might have something like a member ID, action, and article ID. So it's like, what kind of action did he perform on this article? So you have the member ID, and you also have the time. So the other thing that you need to have is on the other side, because you need to have a slicing and dicing by the industry, or where did he come from, what kind of skills does he have, which company does he work on. That's not available in every event because that's too much to put in every event. So you typically have a member profile which stores, this is where at LinkedIn this is stored in Espresso, where you have all the attributes of the member who viewed your article. So the solution is very simple. This is kind of how the old school, or even today, if the data is not really large, you can actually get by with this, where you have an app, you do a join on the fly. So the query is slightly complicated, but you can definitely figure out. You say, hey, how do I join between the two? You join on the member ID, you pull the attributes of the member, and then you are able to group by the industry, and then you get one of the widgets that I showed in the previous screen. This works very well. The couple of problems with this is you can get real time depending on the kind of storage that you use here. So some of the storages, you should be able to keep appending it, and then it should work. In some of the cases, you'll have to do a batch upload into these databases. But the other thing that is really a big con is the latency is very high, because it's doing a join, and then if you look at the article, and if an article is very famous, and there are a lot of popular articles out, so then it's doing a lot of lookup joins across the two, and then it has to scan through a lot of articles to say that what is the number of views that it got, or do slice and dice on that. The second option is a little bit complicated, but I'll walk you through that. So the first part is exactly the same. You get the data, you put it into the activity stream. And then instead of directly putting it into the DB, you kind of join the data prior upfront. So there is a stream processing framework that you put in the middle, where you're doing a lookup as the event is coming in, not at the query time. So you're kind of shifted your focus or the workload from read time to the ingest time, right? So that's a key difference that you want to take away from here. So you look up the database member table, and then now you ingest another event into this. Now this event actually contains everything that you need. It contains the member profile and all the attributes of the member, along with article ID and the action. And now the app is quite simple. It doesn't involve any join, but it can just go through directly query on this single table, and it should be able to aggregate. And the latency part, the good thing about this is it's near real-time ingestion. The second part is I've mentioned it, a low latency here, but again, I've put an asterisk on that. It's unpredictable. The reason is now your cost or the time is proportional to how many rows you're scanning to compute your answer, right? So that's where I'll get back to this on how Pinot addresses this. But you can think of, if the article is not very popular, the time taken to show the analytics is not going to be a lot. But if it is very popular, there are definitely lots of things, especially the ones that ask for a puzzle with how do you answer that? That has a lot of comments and article likes. So those are going to take a lot more time to answer the query. The third is taking it to the next level where you want to get really, really good latency. But what we do here is you pre-cube it. So that means you are more or less computing the answers that you want upfront. So the only subtle difference between the previous one and this, the previous one was just joining and then storing the data as it is. So you can think of one record for every activity that you get. But in this, one record for every activity is fanned out into multiple records, because now you're pre-computing for or p-cubing for all the different dimensions. You might have one row for the geo, one row for industry, one row for, so you're having a lot of fan out. So the problem with this is you are definitely adding a lot more storage. So that's the problem here, which is it's very fast because most of your lookups is just a single row lookup. So your latency is very good. And this is something that people do use. Like Kylin is for example, one of the systems that does the pre-cubing, and it's very fast. But the problem with this is it's very hard for you to get real time in this, because you typically need to end up batching the data. And because you have to aggregate it, and the premise is that for every unique combination, there is just one row. And of course, the storage is going to exponentially increase as you add more dimensions. Any new dimensions, so tomorrow I say that I want to slice by the browser that the user was using or something or some other dimension, you pretty much have to rebootstrap everything. And the query capability as well is not good, because now you cannot do slice and dice or any kind of complex Boolean expressions. You can just simply do an AND. So it is limited in terms of query functionality. So typically, if you want to build something like this, you have all these options that you can pick. And depending on the scale and where do you think the product going, you can pick one or the other. But I'll kind of summarize on what is that you will lose or gain in terms of picking up all these solutions. So the leftmost part is where you started, is a traditional solution where you would pick the join on the fly, right? So the flexibility is huge there. It's amazing. You can pretty much run any SQL query on it. But the problem with is latency. So the complex the query gets, the latency is higher. So you will not really be able to solve this on a site-facing use case. As you move along this axis, so now you have the ability to just do a pre-join and a pre-aggregate. So the latency is getting much better here. But the flexibility is, you're slowly losing all the flexibility, because now you cannot really do a join, so you're just doing a single table query. So the systems on the left side, Presto, BigQuery, Redshift, they are all amazing in terms of giving you full flexibility. They store them as the raw table. You can query them. But you can't really expect a sub-millisecond latency or millisecond latencies, which is what is required, or a strong P99 value. On the middle part, you have something like Pinot, Druid, Elasticsearch, InfluxDB. So all these are definitely the possible solutions that you can pick up today. And if you go all the way to the right, this is basically where you pre-cube everything, and then you can store it as it is. So I put Pinot in this as well, if you have noticed. So I put Pinot in two places. As we get later into this session, we will see why I have put Pinot in both the places. But this gives a crux of what we can gain and what we are going to lose as we pick any of these solutions. So at LinkedIn, once we put all these things together, this is exactly how the architecture looks like. So as the streaming solution, we use the Kafka. LinkedIn is the place where it originated. And then for the stream processing, we use Samza. So that's where we look up Espresso. Espresso is our database where we store all the member profiles. And then it creates this new event, which is the joined activity event, and then puts it into Kafka. And then Pinot consumes it, and then you kind of get article analytics on top of that. The app just simply queries Pinot. So what you saw there in the first, it's basically powered by Pinot, and we have 2 years of retention, but this is something that is configurable, whatever the product decides. And sometimes we might choose to just keep it for longer, but kind of lose some of the dimensions and do some roll-ups. So that was the first part of the thing where I talk. If you look at the life cycle of You basically had the data, and then you kind of generated a product. And now you can also think about, can we do better? How can we use this data in a much more interesting way than just showing it to the user? Can we ourselves use it? So one of the cool things that you can actually do with this data is you can now re-rank our feeds, because as you see, the feed is always like a two-side thing, which is, as a member, I'm going and looking at it, and the article is another side. So you have, as a member who comes in, you have all your connections, and you have all the articles that your connections have written or shared. Which ones do I show you, right? So that's where the feed matching or the ranking algorithm comes in. So a simple option is to just take all the feeds, dump it, and then show it to you, or we can re-rank it. So that is where the second part comes in, which is, can we use all these attributes of the user and the article and then re-rank the feeds, right? So you can look at all these different things, like some of the numbers, how many views, clicks, or what is the age category, and all those things of the age of an article. So you can see all these things and then re-rank your feed in terms of getting. So one of the cool things in this is we saw a huge increase in our engagement rate because of re-ranking, because now it's not static, but it's looks at how many times you have even viewed the article. So if you have already viewed it, then it's automatically hidden from you, and then you're showing a new set of articles. So every time you come to LinkedIn homepage, you might be seeing more interesting articles. So the architecture is pretty much exactly the same, right? So because the only key difference that if you look at it in this is the green things that you are seeing in this, which is the article data and the article table. So now, earlier it was just looking at the member table to do the join. Now we are getting additional features from the article itself, which is which category did it belong to, what was the age of the article. So that's where you have, and the other thing is when you push the event to the Kafka, you are now having additional attributes about the article. So the query looks something like this. And as I said, one of the key things that is super important for us in terms of solving this analytics use case is the latency. So we have almost close to 6,000 queries coming in. So this is not really heard of in terms of analytics use case. So think of analytics, but solving OLTP kind of workload, right? So we have P15, the 50th percentile is almost like as low as 5 milliseconds for us to do something like this. And then we have a very strict SLA of 100 milliseconds, and we cannot really miss that in terms of, because feed is really one of the most, one of the first things that you do as you log into LinkedIn. Most of you might have heard of Pinot as Pinot and Druid. Druid is very popular in this particular space. So a lot of times I get this question of why didn't we use Druid? Why did we build Pinot? So the basic premise of why Pinot started at LinkedIn was to actually serve the site-facing use cases. And if you look at it even today, Druid is not really built for the site-facing use cases. So it's very good for the internal analytics. I'll come to that in the next section. But Pinot has lots and lots of optimization, which is very much geared towards handling the site-facing high throughput at low latency traffic. So some of the key things that we have built in Pinot that attributed to this performance difference is, one is the sorted index. The other one is the per query optimizer. So we have this concept of optimizing the query based on the segment metadata. So for every segment, every small set of data, the query can look very different. It's very different from the traditional SQL databases where it's only the logical plan that is optimized. In Pinot, we actually optimized even the physical plan. And we also have the concept of optional indexing, unlike Druid, which needed indexing for every field. Pinot doesn't really need it because it knows how to optimize whether it's depending on the metadata of the segment. So that's the first part, which is how do we take this data and then generate more products and show it to the users. The second part is what can the internal users do with this data, right? What are the business insights that we can get with the same set of data that we generated? So what we have is a tool internal to LinkedIn called as Raptor, which generates dashboards and insights for pretty much every metric, every business metric at LinkedIn. So we have almost close to 10,000 business metrics that are generated on a daily basis. And it's the same data, so now if you look at it, you can look at where are the clicks coming from, the views coming from by different countries. So the dimensionality is much, much, much richer than what we have on the site facing. So another thing that you can look at, which is how is the grouping by different industries? Is there any change in the trend? Is it coming from software industry, or is it from real estate? Like, what is the distribution and how is it over time? So this is something that is used extensively at LinkedIn internally. Similarly, where did we get the views from? Who was the referral? So there are lots of different dimensions. I won't get into the details of that. But the key thing is we have this ability now to do the same thing for all the various metrics at LinkedIn. So these are all the business metrics that internal people look at, analyze, and then draw some insights, and then they even look at, is there a problem with these metrics? Where can we improve, and all things like that. So there are like lots and lots of data here, and you have the ability to do slicing and dicing, and then roll up and drill down. So the architecture here is slightly different, but it's more or less exactly the same in terms of the only key difference here is you don't really need real time in this. We do have for some use cases, but it's kind of an overkill to have business insights in real time for the internal folks for all the metrics. For the key business metrics, we do have the internal for real time support that pretty much looks like the exact architecture that I showed earlier. But for the offline use cases, we have the two sources of truth. So we have Kafka and we have Espresso. And the data comes into HDFS via a tool called Goblin. So that's the ingestion framework at LinkedIn. And everything is dumped into HDFS. Then we have this pretty cool framework called UMP, which is centralizes all the metric definition and the computation. So the dashboards that I showed earlier, all those things were simply expressed in a language, which is we use either Spark SQL or it can be Pig. And you define the logic and you define the metric here. You say what are all the dimensions that you need in this metric, how often should it be computed, and what is the retention, all those things. And then UMP just simply computes all these things on a daily basis or on a regular basis and then pushes it into Pinot. And then you have the UI on top of it. So the previous screens that I showed you, they were all all the data is coming from Pinot and computed in UMP, stored in Pinot, and then UI, the Raptor is the UI where you saw the dashboards. So this is another comparison between Pinot and Druid in this particular case. So we basically took all these queries and then we ran it across Pinot and Druid. As you see, the P50 and the P90 is not too much of a difference, and this is not really seen by a human, 84 milliseconds versus 136, which is for a human in terms of a dashboarding application, it's not that big of a difference. But as you see, the total time that it took for Pinot to run the same set of queries is almost half of what it took for Druid. So there is a very interesting thing that you can see at a meta level, which is if you look at the same cluster, now you can actually perform a lot more queries using Pinot than in Druid. So, but if you look at a single query and then if you just look at the response time, there may not be too much of a difference in terms of the perception from a user. All right, on to the next. How are you doing on time? Oh, okay, 5 minutes. So the next part is, okay, now we have all these dashboards. Do we want people to keep coming and looking at these dashboards on a daily basis? Because they're just looking sometimes for the trend or for some anomalies and things like that. What if we automatically do that for them? So this is where this is the project that I was working on, which is called ThirdEye. So we built an anomaly detection framework on top of the same data where we are showing as the dashboards. We can automatically start monitoring all that data. So typically what people do for anomaly detection is they build a streaming solution, which is you stream the data and you compute the models, and then you compute anomalies on top of that data. So ThirdEye is a very different architecture. We actually use Pinot as the streaming engine. So we stream the data directly into Pinot. The data is available, and then the anomaly detection is just a stateless system, which simply queries Pinot regularly and then looks at the time series data and then computes the anomalies. So in this provides two things. One is the anomaly detection, and the second one is what we call it as root cause analysis. So if there is a problem, there are two ways to try to do this root cause analysis on that. One is you can have some hypothesis based on your previous things. You might say, oh, the issue was in US last time, or it was in this browser, or based on your prior experience, and then you try to do slicing and dicing. At this point, you're basically guessing where the problem is. So this is a completely different way of looking at the problem. So if you look at it on this side, we just go over the entire data, and then we are able to look at all dimensions at once. And then in one shot, we are able to say where the problem is coming from. So the heat map is helping you guide you towards the things that have issues. So in this case, there was an issue, which is there was an increase of 5% week over week on this article, and we want to know where is this coming from, right? So we have so many different dimensions. How do we look into that? So here it's pretty obvious that you just look at the big one, which is blue, and then the nice thing about this UI is you can click each cell, and then you can deep dive, and then you can go into the next dimensions as well. So it's very interactive. So it's like sub-second latency here, even if it is doing all different dimensions. So if you look at it, it's not one query you need multiple queries to render something like this. So for every dimension, you can think of a different query, and then you have to do a group by across different times. So it's lots of queries that are running, but with the ability that we have in Pinot, we are able to even solve this. So what's the challenge behind the scenes, right? So it's very easy to do an anomaly detection at the top level because you're just looking at the aggregate sum of that metric. But the multi-dimensional anomaly detection is much more challenging because if you kind of unroll it, this is how the loop looks like. Because now you want to try out, is there a problem with any combination of issues? Because sometimes you look at the top, everything looks good. You might not really see an issue that is, oh, there is a problem with Android. That may not really surface on the top. So you want to do all these combinations. So this second part is definitely challenging, right? Because you are now trying to look at all different combinations here, and there is no one key column where you can easily look at a subset of the data. You have to pretty much scan the entire data to compute this aggregation. I'll give you a very small, quick example here on why this is hard. So if your query was, let's say you're trying to detect anomaly in US, you have to pretty much scan, like depending on, assuming most of the clicks and views are coming from US, even though you have an inverted index will only help you find where are all the rows for US. But the scanning, which is the second part of the aggregation, which is the second part, involves scanning all these rows. And that's going to be slow. But the same query for Ireland will actually be pretty fast because there are not many views that are coming from Ireland. So that leads to the part that I was saying that I will get to it later, which is the space-time trade-off. Like if you try to look at all these solutions, whether it's pre-Qube or pre-joined or pre-aggregated, it's really trying to trade off between the two things, which is your space and latency. So the OLAP or the columnar stores like Pinot Druid and Pinot, which is in the similar form as Druid without the star tree index that I'm going to talk about, basically sits there, which is the latency can be variable depending on your input. So for example, in the previous query, US can be very slow, Ireland can be fast. So you have a lot of variability here. And in the other end, you have these pre-Qube solutions, which pretty much the latency is very good because it's more or less looks at more or less becomes a lookup. But then the storage is very high because you're pre-computing a lot of things. So as the number of dimensions increase, the storage cost increases drastically. So you have a steep curve here. So what Pinot added is the concept of what is called as a star tree index, where it allows us to be somewhere in between. So we can either go to that extent or we can be in this extent. So without getting into the details, it's a smart database, data-aware pre-computation. So for example, in the previous case where I mentioned about US, it looks at the data and then it figures out automatically that, hey, if you ask a query for US, you have to scan so many rows. So I'm going to actually pre-compute only for US, but not for Ireland. Because typically the explosion in the pre-cubing comes because you're pre-cubing for every combination without knowing it's going to be expensive or not. So the kind of Pinot now becomes this hybrid solution where you can either go to all the way to this extent, which is super fast, or play very similar to Druid, which is just keep it in raw format. Or you can have this knob, which is for any given query, what is the max number of rows that I can scan. So the configuration is really based on you can say that, hey, for any given query in this form of A equals some value and B equals some value, I should never scan more than 10,000 records. So 10,000 is basically your key there. And that allows you is the configuration part, and that allows you to get the trade-off between how fast you want the queries to be, or you don't want to compromise on the storage space, so you just let it be in infinity. So if you kind of look at that, the left side is basically infinity, that configuration, and the right side is basically 1, which means for any query that I ask, don't even scan more than 1, which comes to the key value part. So this kind of shows the impact of that, because now we are able to run the anomaly detection and the dashboarding, all of these on the same data set. So if you look at it here, Pinot with inverted index, we couldn't really scale more than 10 queries per second with this data, just with inverted, because a lot of these, once you start having anomaly detection, which becomes a machine-generated query, so the load is much higher. But with star tree, we are now able to get a lot out of the same set of machines. Right? So that's the key difference. You might not really see a difference on a per query basis, but a lot of these small differences add up. And over large set of data, you can see a pretty big significant change. The architecture is very similar to the Raptor. The only thing that gets added is the ThirdEye on the top on this end, which is the nice part about this is it's the same data that is doing anomaly detection and the visualization in terms of dashboarding. So you don't really have have to operate all these different systems, and there is no data inconsistency saying that, oh, I detected an anomaly in this, but then now when I go and look at the data, it's something completely different. So all those operational challenges are removed. Pinot usage outside. So this is so Uber is a big time user of Pinot. So they have a lot of side-facing applications. If any of you has used Uber Eats, the restaurant manager actually gets this dashboard for him to look at the analytics on all the Uber Eats, and that's powered by Pinot. Then a lot of internal things at Uber Marketplace, Uber Pool, Uber Freight, Jump, all of them are powered by Pinot on the back. The other thing is Slack. So Slack is one of the users as well. So they were using Pinot Druid earlier. And if you look at the message from them, they basically moved from a 45 node to 80 node. And they still have a lot of capacity. So that is what I was always referring to, that you can actually get a lot more out of the set of boxes that you have from Pinot than Druid. It's funny, both Slack and Microsoft Teams, both of them use Pinot. So on the conclusion side, I think the key takeaway that I would like you guys to think about is most of you have this activity data, and then lots of varying kinds of applications that you want to build on top of it. You might have a site-facing application or internal or anomaly detection. And these applications can start very small, but can become very popular later, right? So the key thing that is most of them end up doing is have different solutions for each of these use cases. So you might use a key value store for one, an OLAP store for one, and the stream processing for another. And this results in a lot of operational challenges and having to build and maintain all these different systems. So our goal was basically to build one system at LinkedIn that allows us to handle and take care of all these variety of use cases. And that's basically what we were able to achieve at LinkedIn. That's pretty much it. I have a few minutes for questions. And then if you're interested in using Pinot at your company, feel free to chat with me. I will be able to help you on what are the things. I mean, the documentation part of Pinot is really bad. That's something that we are working on. But feel free to chat. We have a Slack channel which is active, so you will definitely, and we are also on Apache incubation. So we will definitely be able to provide help in terms of using it. That's pretty much it.
Thank you again. Great talk. So I had a question. You spoke a lot to the effect of latency in terms of how long the query is actually taking to run. But then there's another level of latency, I'd imagine, from creating these pre-computed views. If you were querying like the raw data directly, you didn't have to go through those steps of aggregating all the data. Are there any considerations being made for the amount of, like, how behind, quote, the data is from when it first streamed in by virtue of making all those roll-ups?
Time-wise, it's not a problem because Pinot provides the real-time ingestion. So it's more the stream processing engines are also real-time. So it's a matter of few seconds. So for example, the profile views that I mentioned, you look at someone's profile, it's within 5 seconds, it's generally there, and most of the lag is coming from the Kafka hops in different data centers. But inside of Pinot itself, as soon as the data is ingested, it's available for querying. I do get the second part of that, which is, we are doing these joins, and is it needed? So that's where you want to have the question for the product, which is, what are the things that you can gain out of making it really fast from the user by pre-computing it? So LinkedIn is a classic example where we build a lot of these applications, like 50 plus, and the product managers know the value of how it drives the engagement back and what's the value that you're providing to your customers. So it's really a trade-off. Whether you want to do it for everything, obviously not. That's where, as I mentioned, we don't really have real-time for all the internal metrics. We have almost 10,000 metrics, so only few of them have real-time. So it's really a conscious decision on, are you able to get a value of it? We have the capability. Maybe all the use cases shouldn't be doing that.
Thank you.
What is the data size you have for offline analytics?
Sorry?
In terms of what are the data size of your offline analytics Pinot DB?
So we have more than 100 terabytes of data for the internal ones, because these are all after some time we roll up into a day level. The real-time section, as I was mentioning, for the internal one is much lesser. For the offline ones, we keep the daily for almost 2-3 years, and depending on the retention. So it's
this 100 TB after indexing or before indexing?
It's after indexing. Before indexing, it's probably like in close to a petabyte or something. So there's a lot of compression that you get by indexing and storing it in the Pinot dictionary encoded format.
If I may ask one more question, so this 100 terabytes, right? Are you guys storing it offline somewhere on this DFS or like?
No, Pinot has its own local storage, so it's stored on the Pinot servers itself. It's we keep it in offline just for as a backup, okay. But it pulls it in and then it's served off of local maps. So we map it, we pull it locally and then we map it.
Thank you.
So how does it fare for, so if you have a use case where you have a lot of different, say, metrics, which has each individual diamond, like I will call this as events. So you have number of different type of events which have their own metrics and dimensions. and we have to do like aggregation, like hourly 10 minutes or a daily aggregation. How does it fares? Like, is the Pinot built for these kind of use case?
Yeah, definitely. So but whether you want to do it on the same table or on different tables, that's up to you. So one option that if you want to do it on the same table is you create multiple time columns. So one is on a 10-minute roll to the nearest 10 minutes, and the other one is nearest hour or nearest day. And then using star tree, it will automatically create aggregates for the days and for the 10 minutes or for weeks. Right. So then when you ask for a query which is for a particular 10-minute range, then it goes to the subcycle, the leaf level. Otherwise, it looks at the higher level. So you get a much better. So that's where the per query optimization is very important. So it doesn't have the same plan for every query. And that's where a lot of the performance improvements that you're seeing comes from, that you have that ability to optimize on a per query basis.
All right, one more quickie, and then we got to wrap it up.
Currently, Pinot requires Helix as a cluster manager, right?
Yes.
Is there any plans to support other cluster managers like Kubernetes and other stuff?
I think those are two different. I mean, I worked on Helix, so I can give you a sort of an explanation on how Kubernetes and Helix differ. They're actually complementary to each other. The way you want to look at it is all these containers have a life cycle. So they have one life cycle is just starting and stopping. That's where Kubernetes comes in, which is provisioning and starting and stopping the container. But there are a lot of other things that happen once they start. Like there is a partition, there is a replication, and all those things which Kubernetes doesn't really understand. So that's where Helix comes in. So if you look at Helix and Kubernetes, they're actually complementary to each other.
Okay.
Yeah. So we can use Kubernetes for Pinot, but it's independent of whether we want. We don't have to get rid of Helix to use Kubernetes, so they're independent of each other.